So, welcome to module 2, lecture 2 and 3. So, it is a joint lecture, I mean it is a combined lecture. So, what in the last lecture we have seen? The last lecture we have seen that high level synthesis basically comprises 3 steps: scheduling, allocation and binding. So, in that step we have seen what happens in scheduling, what happens in allocation and what happens in binding. Then actually but we did not give any kind of algorithm to do these steps. So, but actually we have told that the main emphasis of this course is that we will be learning automated algorithms or automated tools which will help you in the design process. So, in the last lecture we have seen some example like A plus B plus C plus D star E, how we can go for scheduling, allocation and binding of this specification. But and we have seen different options where different hardware requirements were there and so forth. But we have not given any kind of automated algorithm which can automatically schedule, allocate and bind these steps given this specification. So, in this 2 lecture series what we will try to do in this or in module 2 on the other there will be 3-4 more lectures, I mean 2-3 more lectures on this. So, in this case what we will do, we will learn automatic algorithms which will do the scheduling, allocation and binding for you, automated stuff. So, given the specification automatic it will be done for you. So, in lecture 2 and 3 first we are going to see scheduling algorithms. So, some automated algorithms where you have to give the specification like A plus B plus C plus D star E is a standard example which you are using or any other specification, and then if you are going for a resource constraint, if you are going for unconstrained, if you are going for time constraint, if you are going for time resource constraint, so you have to give the constraints and then automatically you will get a scheduled output if the schedule is possible. But if the schedule is not possible, you will say that the algorithm will say that it is not possible. So, you have to iterate and relax some of the constraints. So, here what you are going to learn, given a specification and the type of scheduling you want to do, the output is the schedule if the scheduling was possible, and if not, so it will say there is a problem, you have to iterate it. So, we will see different algorithms which can do it for you. Okay. So, I already told you high level synthesis has 3 steps. This one in this lecture we are going to see, the scheduling algorithms which automatically do the steps for us. So, scheduling for unconstrained, time constraint, time resource constraint and time resource constraint, time resource constraint. So, these are the 4 problems already we discussed. So, now we will see algorithms how which we can solve the problem. Okay. So, now before going to this algorithm, so in VLSI as we will prove in the end, the scheduling procedure is a hard problem. So, that is actually it requires exponential time complexity. So, if there are say n operations or if there are n time steps, so time the best if you to find out the best possible schedule, the complexity will be in the order of 2 to the power n. So, you can assume that your specification, if they are having hundreds of variables and your steps may be say hundreds of steps you require to do a practical schedule. So, your complexity will be 2 to the power 100 plus. So, that is actually very infeasible to do this. So, what we do is that these are actually called exact algorithms. So, what do you mean by an exact algorithm? In exact algorithm, so given a problem, so even if you take exponential amount of time or double exponential amount of time, but we will get the exact minimal, that is exact optimal solution, that will actually tell you that this is the best solution possible for a given constraint if the constraints can be satisfied. If it is not satisfied, you will not get the solution, it will say that you have to iterate and change some of the constraints or relax some of the constraints. But if the constraints constraints can be satisfied, so the algorithm will tell you that this is the best possible solution, and it may take a horrible amount of time, because all the problems as we will see in the end. So, start with scheduling problem is a NP complete, or you can call a very difficult problem or exponential amount of problem. So, because of if you know the theoretical computer science, so we can prove that actually this scheduling problem can be mapped to a integer linear program ILP problem, which is known to be an NP complete problem. So, the time taken will be exponential. So, that we can theoretically show in the end. So, you will require exponential number of steps if you want to find out the exact best solution. So, but that is infeasible in many of the time because of the time limit. So, sometimes we go for what you call as heuristic. So, now what is a heuristic? So, heuristic may not give you a best optimal solution, but the time taken will be very less compared to the exponential algorithm. It will be in polynomial time, and actually if the number of steps are n, so you may get the solution in n number of steps, but you may not get the best solution, but your solution will be very near to the optimal solution. So, we call that near optimum solution or near optimal solutions you will get. So, that is actually called heuristics. So, heuristics will be trying different ideas. So, you can think about that. To try to get the best solution, you have to try all possible possibilities. So, it will take a huge number of time to do that. But we can say in a very broad terms, what is heuristics? So, here we will not try all the possible solutions, rather we will try some of the which we tend to think that These are very good solutions and we tend to take them, correct. That means we know that all the solutions, these are all the possible solutions, but we will not try to find out all the possible solutions because of the time, but we may know that this is not a good solution, we may not try this, is also may not be a good solution, not try this, but we will try some of the solutions which we may feel that are good solutions. So that is actually a heuristic, but in that process we save time, but sometimes we tend to find out that we have missed the best or the optimal solution, but in majority cases we will get a very near optimal solution and the time saving will be a huge. So we will be using, we generally use heuristic algorithms for solving this. So for scheduling, first we will see lot of heuristics algorithm and then we will see that what is an exact algorithm like the integer linear program which can give you the best solution or the most optimal solution given the constraints if they are satisfiable, and then we can also show that it actually take a huge number of time to actually, it takes a huge time to find out the solution to this one. So it is a difficult problem and so people are working with heuristics and slowly they are trying to improve upon the heuristics so that with less time they can get, or a reasonable amount of computation time, you can get what you call reasonably near optimal or a solution which is near the optimal. So there are different examples of heuristic algorithms like as soon as possible, as late as possible, least scheduling, forced directed scheduling and all. So and many more. So we will be mainly looking in the lecture some of these heuristic algorithms which actually do not give, can guarantee to give the most optimal solution. They will give you near optimal solution, but the time taken will be very less compared to your exact algorithm which is the integer linear program algorithm. Okay. So we will start as soon as possible. So what is as soon as possible? As soon as possible, as the name suggests, it is nothing but you have to decide on a number of time steps, say 4 time steps or 5 time steps, then you actually schedule all the operations as early as possible. So obviously like if you look at the example in the last lecture, like O1 plus O2 plus O3 actually will be multiplied by O4, that is the multiplication. So here you can see, but O1, O2 and O3 they cannot be done together, like our example was A plus B plus C plus D and you have to multiply with E. Okay, so A plus B will be together, C plus D will be together, then you this generates temp 1, this will generate temp 2, then they have to be done in a separate step. So this can be done in step 1, this can be done in step 1, but temp 1 and temp 2 which is generated by this one cannot be done in time step 1. So that has to be done in time step 2. So even if you take the as early as possible condition, so here we actually decide what is the maximum number of time steps allowed, then what we do, we schedule as early as possible, but all the operations cannot be done in time step 1 because of the dependency, but still maintaining the dependency, you have to find out we can as soon as possible we can do. So in this case what you are going to get, so you can think that here we will be able to minimize our time requirement. So that is basically one kind of a schedule. So as whatever I discussed is written over here. So first we determine the maximum number of steps, then we schedule one operation in one steps as early as possible, but here you have to satisfy the partial order, that is already we have seen, because there should not be any violation of data dependency. So if we all these are, if the algorithm, all the operations can be allowed in the time steps, so if we say like 3 times step or 4 times step, then you can say a time constraint schedule, so your job is done. So and as soon as possible, obviously do not consider any resource constraints because we are doing everything as soon as possible. So obviously we may land up in taking a huge number of resources. Okay, so now we will first see the algorithm in a more formal way and then we will see with example how it actually operates. Okay, so what is the input? So O, a number of operations set O, maximum number of control steps. So you can take 3 or 4 or whatever. Then what is the output? Control step will have to be given for each of the operation and status of scheduling. Like if you take a very short time step which is non feasible, so you will say that the schedule is non feasible, and if it is possible, so it will be possible. Now what do we do for each operation OI, so you take each operation one at a time you have to do. So you have to find out if OI has no immediate predecessor. Okay. So, you have to first find out all the operations which do not have any predecessor, that is they can be computed from the inputs itself, like our previous example A plus B plus C plus D. So, A plus B and C plus D can be done in time step 1 because they do not have any predecessor. So, this was our actually O1, this was O2. So, O1, O2 can be scheduled in time step 1 because they do not, O1 and AB and CD are taken from inputs, they do not require any predecessor. But multiplication you require temp 3, that is actually O1 plus A plus B plus C plus D, that has to be multiplied with C, multiplied with E. So, you cannot schedule the multiplication operation in the first time step because multiplication operation has some predecessor. So, what is the predecessor? It is the answer of A plus B plus C plus D. So, in the first time step what we do? We allocate control step 1 to all the operations which can be computed from the input. So, it is saying that if OI has no immediate predecessors, then you do that. Otherwise, what you do? Otherwise, you assign control step say element or say another operation operand, actually operation has a predecessor. So, you have to first schedule its predecessor, then only you can schedule the element. So, it says that for a OI which has a predecessor. So, you say that control step OI is equal to maximum of control step of j, sorry, non step j plus 1, where OJ is the immediate predecessor of OI. So, it says that this is OI, and so there may be an immediate predecessor, maybe many predecessors OJ. So, this is a OJ, this can be also OJ. OJ, the different predecessor, like it actually OJ belongs to immediate predecessors of A. So, I mean what you have to do, you have to find out which is the maximum one. So, it may depend on this, it may depend on this. So, it may be in time step 2, it may be in time step 2, but it may be in time step 3. So, what you have to do? So, obviously, you cannot schedule it in time step 3 because it is dependent on this element which is having a time step which is in time step 3. So, you cannot do it in this one because OI actually depends on the value of this node. Okay, so, what will be the time step here? It will be 3 plus 1. So, that it is saying. So, you have to find out the maximum of the control step for all the predecessors of OI, and you have to add 1. Okay, and then finally, if you have to repeat this for all the elements. So, what we do? First schedule all the elements at time step 1 which can be directly computed from the input. Then we find out all those operations whose immediate predecessors have already been scheduled. And then you have to find out which is the maximum among them, you have to add 1 to them, then that element is also scheduled. You have to keep on doing it till all the operations are over, and if in the end you find out that we could do everything within M. So, the maximum control step of OJ, that is the last element, is less than equal to M, then the study is successful, else we are not able to do. Okay. So, we will take this example and do this. So, this is a bit different example than which we have considered in the last lecture. So, it is what is A star B by C star D minus A minus E star F by B. This is one output, big expression, and this is the second output. Okay. So, we are taking a bit complex one because we have to illustrate the cases. So, in this case you see A star B, C star D. So, so, and we have taken say M equal to capital M equal to 4. So, you can easily will see that it cannot be done anything less than 4. So, it is 4. Now, we have to do what? Now, you have to schedule as soon as possible. So, we have to schedule elements which are actually, so we can say that this one you can say is O1, C plus D we can say that O2. Then what we can say, okay, let us go through it figure, it will be more clear. So, A plus B is O1, A C star D is actually O2, then this divide by is actually O3, then what is O4? This whole stuff actually subtracted by A becomes O4, and then actually this E star F is O6, this divided by B is O7, and finally when you subtract this whole stuff it becomes O5. So, actually these are some of the names we have given for the output. G plus B is actually O8, and finally addition of this is O9. So, this expression we have given the numbers in the slide itself. Now, you have to find out as soon as possible, and M is equal to 4. So, you have to find out which we can schedule immediately at step 1. It is possible only when the variables or the operations which do not have any predecessor. So, A plus A star B can be done because they can be computed from the input. C star D can be done because they can be computed from the input. Okay, but this one A star B by C star D minus A, this subtraction operation we cannot do immediately because it depends on the output of these two. Okay, so, this cannot be done immediately at stage 1. Now, also E star F we can do immediately. So, we have put E star F, O6 we have put in time step 1 because there is no immediate predecessor. But this by B also we cannot do it right now because it depends on the output of E star F. Now, for this other expression we know that G plus B can be done in time step 1 because the variables are directly as input, and O8 can be scheduled in time step 1. So, these are the variables operations like O1, O2, O6 and O8. So, we can schedule them in time step 1 because they do not have any predecessor, their values are directly from the input. Now, you see, now we will find out that A plus B star B, C star D, this division operation can be now scheduled in time step 2 because it requires A star B and C star D which has already been done. So, the predecessor of O3 is O1 and O2 which has already been scheduled in time step 1. So, just add 1 to this one. So, the time step of O3 will be 2. Similarly, for O7 the predecessor is temp 5, that is the output of O6 which has already been scheduled in time step 1. So, you can easily schedule B in time step 2, and to time step will be time step of O6 plus 1, so O7. Similarly, for this case, like for this addition operation, you know that G plus B, G minus B already scheduled in time step 1, and O9, that is this addition operation plus F can be now scheduled in time step 2 because it depends on O9 depends on O8, O8 already scheduled in time step 1. So, you add 1 to time step 1, you get time step 2. So, O9 is scheduled over here. So, actually we are pushing everything as early as possible. So, now this thing is done. So, now if you look at it, so output is already 2 is generated. So, this part is over. That you know that O4, you have to observe that O4 that is subtraction operation with this one. This cannot be done in time steps 2 because predecessor of O4 is O3, because O3 has to be done before O4. So, now as already O3 has been scheduled in time step 2, so in time step 3 we can schedule O4. Similarly, the last stuff, that is this subtraction operation O5, this can only be done in time step 5, that is time step 4, that is 3 plus 1, because for O5 we have two predecessors, one is O7 and one is actually your O4. So, we have to take the maximum one, because O7 is already scheduled in time step 2, but still another dependency of O5 is O4, which is done in time step 3. So, you have to take the maximum one, you have to add 1 to it. So, 3 plus 1 is 4 and O5 is scheduled in this one. So, in this way we get as soon as possible schedule. Now, you have to compute how many resources you require. So, you see that 1, 2, 3. So, in this parallelly 3 multipliers are required. So, 3 multipliers will be required over there, 1 subtractor is required over here. So, here 2 dividers are required over here. So, 2 dividers are required over here, 1 adder is required over here. So, these two subtractors can be reused from here. So, resource requirement is 3 multipliers, 1 subtractor, 2 dividers and 1 adder, because whatever is in one time step you have to do it in parallel. And if you look at the registers, we are not considering here, but the number of registers will be 1, 2, 3, 4, 5, 6, 7, 8. 8 registers are there and they can be all reused in the other variables in the other time steps. Okay. So, now we will go to the another schedule. So, as already said, so what are the requirements over here? So, requirements over here 3 multipliers and 1 subtractor in first time step, 2 is second step is 2 divider 1 adder, and third step for and fourth step we do not require additional hardware, they can be reused. So, in all we require these are the resources. So, whatever we have already told is actually listed out in this slide, you can go through it. Now, we go to another extreme mode of schedule. So, that is actually called as late as possible. Now, in this case what we have done, in as soon as possible what was our idea? In as soon as possible we have tried to, what we have done? We have tried to schedule as soon as possible. We have taken m equal to 4 and we have tried to push everything as soon as possible, or in the first time step. But you have to observe here that if we say that our time step would have been 3 over here, if we say that our m is 3, so it would have resulted in a infeasible situation, because this O5 cannot be scheduled over here, because it is dependent O4 which is again dependent on O3. So, O3 cannot be done in 1, it is mandatory to be done in 2, O4 cannot be done in 2, it is mandatory to be done in 3. So, if you make that time requirement is 3, so this would have led to a infeasible situation. But now we have taken m equal to 4, so we got a perfectly correct schedule. Now, in case of as late as possible, so what we are going to do is very similar to as soon as possible, but what we do again here, we say that we actually take the maximum number of control steps. Then actually what we do, we try to one at a time and then as late as possible. So, in this case what we do, try to push, in the earlier case we are trying to push as early as possible over here. In this case what we are going to, we will try to keep things as low as possible. We will take this m as the what you call the maximum one, and then we will try to keep elements over here and slowly grow over here. That is, we will try to push the elements in this direction, that is in the lower direction. Okay. So, now again when we will consider it to be successful, if we find out that all the operations has been scheduled within the first control step, because we are going reverse, then it is done, otherwise it is not done. Okay. So, we will again look at the formal algorithm and then we will see with an example. Same thing, the operations, same thing as the algorithm, operations will be given, maximum number of control steps will be given, and output is the control steps for each operation and status. So, again like the earlier case, for all operations what you have to do. So, now again we are going as late as possible. So, we have to just find out all the operations OI which do not have any immediate successor in this case. So, if you look at this, which do not have any immediate successor, O9. So, O9 is actually an output, O5 is an actual output. So, they do not have any kind of a successor, nobody depends on them. So, what we can do, we can schedule them as late as possible. So, that is what they are saying. Okay. So, you see if Y has no immediate successor, that is the computer generated outputs, you schedule that at the last step. In the previous case what we are doing, we are trying to find out all those operations which do not have any predecessors, and we are trying to put it in the first time step. Here we are doing just the reverse, we are trying to find out all the operations which do not have any successors, and we are putting in the end. Next what we are trying to do, then we are trying to find out all the elements, say this is J has been scheduled over here, okay, that is last step or some intermediate step. Then you need to find out all other elements actually whose successor is OJ. Okay, so OI actually is OJ is the immediate successor of OI. So all OIs will find out whose immediate successor is OJ. Okay, and then we will try to schedule it just one step before it. So it is control step OJ minus 1. OJ is the immediate successor of OJ. So OJ is scheduled. Now you find out all, sorry, OJ is scheduled in the one time step. Now you find out all OIs, sorry, these are not OJs, all OIs who actually are immediate predecessor of OJ, and you just schedule it one step behind this, before this. So you just want this one. 1 minus you have to do for OJ. Then if all OJ are scheduled within the first control step, if you can do everything in the first control step, then the strategy is successful, else it is not successful. It is very similar. So we will just see this and then we will same example. So again same example is like this. So in this case you have to go the reverse way. So you know that O9, that is this addition operation, and this subtraction operation O5, they just generate the output. So you do not need to worry at all about anything. So what you can do, you can schedule at time step number 4, because already we have seen that you should not consider time step 3, because for this scheduling problem 3 will result in an infeasible situation. Okay, so in last step we are allocating 5 and 6. Now what do we do? So now you know that already this has been scheduled. So we are putting it as late as possible. So we are trying to push it down. So now you see that. So as this has already been done. So now G plus G minus B, that is 08. So immediate predecessor of 9 is 08. So you can schedule it at the time step 3, that is 4 minus 1 is 3, just you put it over there. Now in time step, now in this case you see what is the immediate predecessor of 05, that is actually 07. Okay, so 07 is what? 07 is this actually this division operation, that is E minus F by the division. This division operation is actually 07. So now what happens? So just one step before this 06, you just schedule it at time step 3. Similarly 04, this 04 is what? This 04 is actually this subtraction operation, this whole stuff minus A. So it is also the predecessor of 05. So just schedule it one step before this, that is will be time step 3. So in time step 3 we are scheduling 04 and 07. Now if you go by this, similarly if you go, so what is 07? 07 is actually this division by B. So one step before this is actually E star F. So this is actually E star F, that is 06. So one step predecessor of 07 is 06. So you just schedule it just one step before that. So in time step 2 you have scheduled. Similarly for 03 and 04, 03 is just immediate predecessor of 04. So you just schedule it one step ahead. So it will be 03 will be here, and similarly 01 and 02 are the immediate predecessors of 03. So you have to schedule them over here. Now you just look at the situation. So this algorithm was very simple, just the reverse of as soon as possible we have done. But let us see how many requirements are there. So here we require 2 multipliers immediate. Here you same multiplier can be reused. So you require 1 divider over here. Okay, here you require 2 subtractors. Okay, this divisor can be reused. Okay, and here you require 1 adder. So this is what is your requirement. So now you see an interesting thing. So in the old case we require 3 multipliers, but now you require 1 multiplier, 2 multipliers. So we have saved 1 multiplier, that is very important. But on the other hand, we have actually lost 1 subtractor. So if you just look at it, so we required 1. What do you required? We required 3 multipliers, 1 subtractor, 2 dividers, 1 adder. So now in this case we have done a great deal of saving. So in this case what we have saved? We have saved 1 divider, we have saved 1 multiplier, we have saved, and 1 subtractor we have lost. But you already know that subtractor area is much less than divider hardware or multiplier hardware. So we have achieved a great deal of optimization by going for as late as possible schedule. So in this example we have scheduled everything below the end. So we have got a very good schedule where we have saved some element. Now what we have lost? So we have lost 1 subtractor. So let us see what we can do to actually save our subtractor. So if you remember that this case, the 2 subtractor case, we got 1 subtractor when our solution was as soon as possible, and this and this things adder there was no change, but this multiplier and divider we saved when you are going for as late as possible. So let us try a bit different heuristic. So actually what we are doing, they are all heuristic algorithms. Nobody will guarantee that you are always going to guess this. If you are going to use as late as possible, for all examples you are going to get the best solution, and for as soon as possible, for all cases you are going to get the best solution. Heuristic means for some cases solution A will be good, algorithm A will give a better result than algorithm B, and the situation will change with a different example. So in this example let us divide it into 2. We will see that. So in this case what we have achieved, that is written 2 multipliers, 1 divider, okay, and 2 subtractor and 1 adder. So these are the great saving we have, and only 1 subtractor has been deprived. We have required 1 more subtractor. Now we will see what we can achieve more, but because we should not have the feeling that as soon as possible is always very bad and as late as possible will always give you a better result. Had it been the case, we should not have lost 1 subtractor over here. It should always have been the gain. So in different examples, one will give a better solution than the other, and so forth. So we will try to make a hybrid of these two and see if we can get anything better. So, heuristics are like this, they are not exact algorithms. So, always for different examples you may get different solutions, different solution in terms of quality. So, if you are comparing as soon as possible and as late as possible, so we saved one multiplier, saved one divider, but increased one subtractor. This is what has been happened. Now, what we are going to do, so whatever is written over here, let us try. So, let us try to separate this. Okay. So, you see that multipliers and dividers are actually are already incurred for this part of this problem. Like if you see that the two subparts actually out 1 and out 2. So, you can see here that out 1 actually is involved with adders and multipliers and dividers, but out 2 is involved with subtractors and adders. Okay, so, we saw that the subtraction requirement was increased when you gone for as late as possible, and divider and multiplier we got better solutions when we gone for as late as possible algorithm. So, let us partition this into 2 and let us try to apply as late as possible here and as soon as possible over here. Okay. This is one another type of heuristic we are thinking. Let us see what happens if we do that. So, in this case let us see. So, it is as late as possible. So, obviously this structure will be similar. So, these two we could have put it over here and here, but as it is as late as possible. So, we are bringing it just towards the down. And if you observe that as late as possible, so we had the adder over here and the subtraction over here. Now, we are going for as soon as possible. So, we are moving it towards the upper end of it. Now, let us look at the resource requirement. What happens? So, you require 2 multipliers, 1 subtractor in the first case, and then 1 divider over here, because you can reuse multiplier, you can reuse 1 adder you require. Okay. 1 adder you require in this case, and here the multiplier subtractor can be reused, this subtractor can be reused over here, the divider can be reused from here, and subtractor can be required. So, now this is your resource requirement. So, it is 2 multiplier, 1 subtractor, 1 divider and 1 adder. So, this is the most optimal solution we would have got. So, you see that as late as possible if you apply over here, and as soon as possible if you apply over here, you are getting the best solution. So, I mean most optimal solution for these examples. So, what is basically you are essentially want to show that as soon as possible and as late as possible are actually heuristic algorithms. They are not exact algorithms. So, for some example one will give a better solution and from case other will be giving you a better solution. So, what next? So, next we will try to design another heuristic which will actually take a hybrid of as soon as possible and as late as possible. So, I mean it is very difficult for us to first try as soon as possible in one part of the circuit and then try as late as possible in the other part of the sub circuit, and then find out which one of them gave a better result. Like in this case we first tried as soon as possible, then we tried as late as possible, then we found out for this part of the circuit apply as late as possible, this we apply as soon as possible. This is a very difficult way of solving a problem. So, if next we will see another heuristic which is actually called force directed scheduling, which is actually a hybrid of as soon as possible and as late as possible. So, what it will do, as we will see in the heuristic, so it takes ideas from both of them and final solution will be automatically wherever possible, wherever it will be good as late as possible will be applied, and wherever it is bad, I mean appropriately things will be applied. So, what is the resultant effect of this heuristic? So, in which part of the circuit, if in a part of a circuit if it finds that as soon as possible is better than as late as possible, so automatically as soon as possible will be applied and vice versa for the other case. So, that will be happening automatically. Here we have iterated to as soon as possible, then we have gone for as late as possible, and then we have tried a hybrid of both. With one part we have applied one, in the other part we have applied one. So, this is a very bad way of doing our algorithm. So, now we will see the algorithm, in which case that will be automatically taken care by the hybrid nature of the algorithm. So, automatically for which part of the circuit it is required, that heuristic in between as soon as possible and as late as possible will be selected. So, this is what our discussion was about as soon as possible versus as late as possible. So, finally, we achieved this one, which is the best solution: 1 adder, 1 subtractor, 2 multipliers and 1 subtractor. Okay. So, 2 multipliers, 1 subtractor. So, these are the resource requirements and these are actually all reused. They are all reused. Okay. So, that is what we have said. So, now we will be combining as soon as possible and as late as possible. So, that algorithm is called force directed scheduling. So, what is that? So, what do you do in force directed scheduling? In force directed scheduling, what we will do? So, first step it will actually go for as soon as possible schedule once and as late as schedule ones. So, you have to see in last case also what we have done, we have gone for as soon as possible, then we have gone for as late as possible, then we are trying to find out which part of the circuit which is better. So, that is actually a very what you call a fuzzy way of stating something, that you find out which part of the circuit or which sub part of the circuit which is better. So, here actually we are going to make very crisp steps of the algorithm. So, what is our idea? Our idea is that we are basically trying to find out in which part of the circuit which is a better algorithm. So, obviously what you have to do, you have to apply first as soon as possible and you have to first as late as possible, and then try to do some hybrid among this. But the hybrid nature what we are trying in the last example was not good. That is, manually we are trying to find out that this part of the circuit this is good, that part of the circuit that is good. That is not a very good way of doing it. So, what we will do in force directed scheduling, we start by as soon as possible and as late as possible. So, we do that. Okay, then what do we do? Then we find out some flexible operations. Like what do you mean by flexible operation? Like if you look at this, this thing. So, if you see, these are the only operations where there is flexibility. That is, you can move this 2 steps up or 2 steps down. Similarly, this can be moved from here or here. But this part of this, what you call schedule tree is almost fixed in as soon as possible and as late as possible. So, there is no flexibility over here. So, either you apply as soon as possible or either you apply as late as possible to this sub part, nothing is going to change, because you cannot move any of the operations. So, your m is given to be 4, that is assumed. So, within this m equal to 4, you cannot move this operations. So, this is actually you can either select as soon as possible or as late as possible and fix it. Okay, so that is actually saving some of your computation effort. So, if you think that in the whole circuit first I will try as soon as possible, then I will go for as late as possible, then I go for some hybrid in the whole part of the circuit, that is will actually they will take more computation time. So, what we have found, what is the first step of force direct FDS schedule? You will first go for as soon as possible, then you will go for as late as possible. Then you will try to find out which part of the schedules is fixed, that is there is no movement. So, in as soon as possible or as late as possible, nothing could be moved. For some operations the schedule is same. That means what? There is no change in the schedule if you apply as soon as possible or as late as possible. So, both of them are going to give equivalent results, or in other words they are non-flexible, you cannot move, they cannot move from their position. So, you better fix them and try the heuristics with this type of nodes or this type of these type of operations where there is movement flexibility. Okay. So, now that is the first step. So, you say that we give actually a range. So, what is the range? So, the range is actually control step assigned by as soon as possible to control step played by as late as possible. Like for example, in this case this guy can be scheduled over here or this guy can be scheduled over here. So, its range is 1 and 2. So, this guy can be scheduled over here or this guy can be scheduled over here. So, its range is 2 and 3. So, this subtraction operation can be scheduled here, here or here. So, its range is between 1 and 3. Similarly, this one can be scheduled in 2, 3 and 4. So, range is 2, 3 and 4. So, you just find out the range first. Then what we do, then we take each type of operations one at a time, like addition operations, then multiplication, then subtraction, then division, something like that, and then try to freeze one at a time, because you see what is the basic motivation here. So, actually adder cannot do a subtractor, that is the assumption. So, in a very advanced paradigm, adders can also do subtractions and subtractors can they are actually same elements, and also you can think that multipliers can also be treated as dividers and dividers can also be treated as multipliers. So, sometimes we have general purpose blocks. So, but for the simplicity here we are assuming that adders can do only addition, subtractors can do only subtraction and so forth. So, what we are trying to do? So, if you are parallelly scheduling one addition, one multiplication, one subtraction and one division, you are not had any problem, because you require one block each. But if you are in one time step, if you are parallelly assigning what? If you are parallelly assigning 2 multipliers or 3 multipliers in one go, then you are at a problem, because then only you are going to require more number of hardware elements. Like in time step 1, if you schedule 3 multipliers, then you require 3 multiplier blocks. So, you can understand that the heuristics FDS thinks in this way, that we take only multiplier operations at a time, optimize it, then go for subtraction, then optimize it, then go for addition, optimize it and so forth, because in a very broad sense, you can think that the optimization of the dividers will not have much impact on the optimization of the adders and so forth. But obviously, there will be some impact that we will see in the end, because if you fix one operation in one step, then actually flexibility of the other operations will get changed because of that, and then there can be some problems. So, that we will be looking at in the question and answer section, but broadly you can think in this way, that if you are talking about optimization of adders, just think about adders. If you are going for multipliers, then just think about multipliers and so forth, because we have to think of, because if you are consuming 3 hardwares, 3 multipliers in one time step, then you require actually 3 hardware, 3 multipliers. But if in a single step you add schedule 1 adder, 1 multiplier, 1 subtractor, 1 divider, then that is not of a concern. So to do this, operations of each type are considered one by one. For each given type of operation, the total requirements of the operations under question have to be minimized. We select the combination that led to minimum number of operations, and then when we are done with one type of operations, we go for another. So what basically says that we first take multipliers and then we try to make a schedule such that multipliers, minimum number of multipliers are required, then once the multipliers are done, then we go for adders and so forth. But actually, I mean, this will not always lead to an optimal solution, because sometimes when you are thinking about the multipliers only and we schedule some multiplication operation, but based on data dependency, the flexibility of the adders or the flexibility of the subtraction operations may also get changed, and so sometimes we may not get the most optimal result. So that will be very much clear when you will take the example in case of the question answer session. But for the time being, just think of this heuristic idea is something like this: take an operation like adder, multiplier, subtract one at a time, optimize one and then go for the other and so forth. Okay. So before we go to the exact algorithm and the examples, let us define some, formally we have to define some variables or some parameters, like as soon as possible I, that is the actually control step to operation I by as soon as possible algorithm. LAP I, so what does it mean? Control step assigned to operation I by LAP algorithm. What is interval I? That is as soon as possible to as late as possible, because say as soon as possible to operation 1 is 1 and as late as possible to operation 1 is say 5. So interval I is equal to 1 to 5 kind of a thing. So what is range? Range is equal to as late as possible I minus as soon as possible I and 1. So if it is actually as late as possible is 5, this is 4. So what is range? Is say, sorry, this is 1. So 5 minus 4 plus 1. So range is actually 2. Sorry, 5 minus 1 plus 1, so range is actually 5. So that means range says that within what is the distance or what is the boundary in which an operation can be flexibly scheduled. Then probability Ij is actually the probability of scheduling an operation Ij in step j, operation I in step j. And what is step j? So step j should be in interval I. That means what? Actually, so if there is this operation OI, okay, so now it says that, say the time step 3 say, so now it is a probability Ij says that what is the probability of scheduling operation 2, so this is operation 2 in time step 3. So that is what? That is actually then what should happen? That time that operation 2 interval should be within 3 should be within an interval of O2, because O2 should be feasible to be scheduled in time step 3. So that it says, and what is probability of this one is actually 1 by range. Okay, so in this case we assume that, so as soon as possible the schedule was 1 and this was actually 5. So range is actually 5 minus 1 plus 1, so this is equal to 5. So what is the probability that say this operation is scheduled in a time step between 1 to 5 is actually 1 by the range, that is 1 by 5. So it is actually, so this is actually 1, 2, 3, 4, 5. So 1, 2, 3, 4 and the one step is 5. So it can be scheduled from here and here, anywhere it can be scheduled. So what is the range? Range is actually 1 to 5. Okay, so that is range is 5. Now what is the probability that it will be scheduled in any time step between 1 to 5 is actually 1 by 5. That is what is the probability it is saying. Okay, so now that is about the probability of Ij. Then finally we have another thing is called the list Kj. So what is the list Kj? It says that set of all operations of type K in step j. That is actually say in this step. So you can schedule say one multiplier operation, that is Oi is multiplier operation. Then you can say that Oj is actually the addition operation and so forth. So it says that in time step j, set of all operation types K, that is can be multiplier, adder, subtractor, divider, whatever is possible in that time step. So that will actually call the list j. And obviously, I mean that says that that is set comprising all operations of type K such that j belongs to interval I. That is what I have told in informal words, that is it says that list I in a time step will say what are the different types of operations which is possible to be scheduled over there. Finally, the last is actually cost Ik. So that is number of operations of type K required in step j. That is, say for example, in one step you require say 2 multipliers. So the cost will be actually 2 of type multiplier. So that is actually the cost, and this is actually the formula of calculating this one, that you have to summation all the probability values. So just take this expression. So whenever we will be illustrating with example, this mathematics will become very clear. Now what is actually force directed scheduling will do? So what I feel is that I will first go to the example, then I will come to the algorithm. Okay, then it will be algorithm and the steps, because otherwise the algorithm is a bit more mathematical. So first example explaining with steps is a very good idea of doing it. Okay, so This is our old example we are going to take, and so what is the thing? So, we already saw that operation 1, 2, 3, 4 and 5. So, these operations have no flexibility in as soon as possible or as late as possible. They are actually hard coded in the different times. So, what? So, range of 1 is 1 and range 2 is 1. Why? Because it is 1 and a 1 and a 1 and a 1 for O1 and O2, because they cannot be shifted. So, in case of range 2, what is the interval? So, interval is actually sorry, the range is 1. In this case, you can write 2, 2. I am sorry, this is 3, 3, and you can write is 4, 4. Sorry, this is some for some of the issues over here. So, it is from 1 and a 1, 1 and a 1. So, what is the what will be your range? So, range in this case will be 1 minus 1 plus 1 kind of a thing. So, it is 1. So, in this case, what also 2 minus 2 plus 1 is a 1. But whatever what do you mean by range equal to 1? So, range equal to 1 means there cannot be any kind of movement for this one. Interval means, so as soon as possible time and as late as possible time. Okay, so in this case it is fixed. So this part let us not bother about much, because nothing can be done over here. Now let us look at the O6. So we saw that O6 can be scheduled over here. Also O6 can be scheduled over here. So actually O6 can be scheduled over these two places. So it as soon as possible is 1 and as late as possible value is 2. So what is the range? 2 minus 1 plus 1, so that is equal to 2. So range is 2. Similarly, O7 can be scheduled in time step 2 or time step 3. So it is 2 or 3. So what is the range? So it is 3 minus 2 plus 1, that is again nothing but 2. So the range of this one is 2. Okay, and now if you look at this operation 8, so it could be scheduled here, here or here. So the as soon as possible is 1, as late as possible is 8. So if you make a difference, so it is 3 minus 1 plus 1. So it is range is 3. So range is 3 about it, and similarly for the 9. So this is your range. Okay. So this is your actually different ranges we have computed over here. So that is actually the for computation of the ranges. So in different time steps. Okay. Now next we are going to see what is your list. So if you look at it, so what will be your list over here? So in this case the list will be multiplier, multiplier, multiplier and subtractor. What will be the list over here? So list over here will be divider, multiplier, divider, subtractor. So this way you can find out your lists. Now what we will go for optimization one step at a time. Okay, so this we have found out. Now what we are going to do? We are going to take one operation at a time. So what is the one operation at a time we say? Let us start with the multiplier operation. Okay. So what is the multiplier operation? We will start. All these mathematics will come back and we will reiterate and tell you. So what is the multiplier operation? So the multiplier operation is actually this one. So what is the probability that it will be scheduled over here? It is half. Okay. So what is the probability? That is the formula. Let us see what is the formula for this one. So what is the formula we have seen? The formula of probability of scheduling it here is actually 1 by 2. That is the range. Again this one will be range. So it will be actually 0.5 over here and 0.5 over here. The scheduling property, that is the probability of scheduling the multiplier in this step is 0.5 and in this step is 0.5 because 2, and this divider is also 0.5 over here, 0.5 over here. The subtractor is 0.33, 0.33, 0.3. That is very obvious, is 1 by 3. Again this one is 0.33, 0.33 probability of scheduling this over here. Okay, and all here the probability is actually 1, 1. You should also count the probabilities will be 1 because they do not have any flexibility. Now we will take the case of a multiplier and see where the multiplier is to be scheduled. Then you can forget about all others. So you see the multipliers can be scheduled, this multiplier can be scheduled here or it can be scheduled here and nowhere else. So here if I put the multiplier, so the probability is 0.5, this is a 1. Okay. So if I put the multiplier over here, so what will be the probability become? The probability will change from 0.5 to 1 and the number of multipliers required will be 1 plus 2 plus 3. So it will be 1 plus 2, 1 plus 1, so that will be equal to 3. So initially it was 2.5, so 1 plus 1 plus 2.5, so now it has become 3 over here. Okay. So and so it has changed from 2.5 to 3 if I schedule the multiplier over here. So if I schedule the multiplier, initially what is the probability here? It is 1 plus 0.5. So initially it is 1.5 the probability. Now if I now schedule this guy from this multiplier from here to from 1 to step 2, so it will be 1 plus 1 over here, then it will be time step will be actually equal to 2. Okay, and there is no other multiplier over here. So this actually stops my computation for multiplier. Now you see, if I put my schedule my multiplier here, the probability cost, actually I should tell about the cost because that is actually the summation of the probabilities. So cost will be what? So in this case the cost is 1 plus 1 plus 0.5, which has changed to 1 plus 1 plus 1, so it is 3. And here if I schedule it here, so what will be the case? It will be 1 plus 0.5, it will be changed from 1 plus 1.5 to 2. So, you see in this case it is 2 and in this case it is 3. So, in this if I schedule this in time step 1, the maximum cost will be 3 and in this case it will be 2. So, obviously I will go for scheduling this guy over here because the cost of the multiplier will be 2 over here. So, a multiplier case is done and this is scheduled over here. Now, if I see, if I schedule the multiplier over here, then a very interesting thing will happen, then this guy will be fixed over here. Then the flexibility of this divider is no longer there. So, it will be actually fixed over here and its range will be fixed. You cannot do any kind of changes with it. Okay, so, that is actually it has one, in this case it has done you are good because you have scheduled your what do you call this multiplier over here. So, it is pushing down this one and so you are also saving on the divider range. But this constraining that you are scheduling this first is actually constraining this here may not sometimes give you an advantage. Here you are getting a very good advantage because this multiplier you are scheduling it over here. So, divider is pushed over here. So, you can reuse these dividers. Okay, but had it been for some reason this is scheduled over here. So, that may lead to some other case that we will see in the example in the question answer station. Okay, but what essentially has happened that this you have scheduled over here to reduce the probability and this has actually pushed it over here. Okay, so, this is now fixed. Now, its range will be 1, its range will be 3 and it will be 1. Now, we can take another operation which is the divider operation and finally, we will go for the adder operation and it will do it. Okay, so, that is the basic idea. So, now we will go for the formal algorithm. Okay. So, now what we are going for the formal algorithm. So, what are the inputs as soon as possible and as late as possible, then control step you have to give an output and you have to give the scheduling. Okay. So, now what you do using the as soon as possible scheduling for all operations you compute interval, range, probability, least and cost. So, whatever variables with that we have already done, we have to do that. Now, for each operation k. So, now here actually operation type. Okay, so, it is very important. Now, we are going for type of operation like adders, then multipliers, then subtractor, divider, or in the other way you go for multiplier, subtractor, divider and so forth. So, for each operation you repeat. So, what do you do? First you said that the base case is best value or the cost base is infinite. Say for example, the cost of some resource you consider to be infinite and then you initialize the best step to be 0. So, this is the initialization step. So, initialize we say that the cost required is very, very high and the best step is 0. This is no step 0. So, this is the initialization operation. Now, what we do? Now, for each operation of type k whose range is greater than or equal to 2, because if range is 1 already we have seen that there is no flexibility in movement. So, we should forget about them. So, wherever they are scheduled their probability is 1 and they are scheduled over there. So, you can just keep it over there. So, you need not bother about those cases. So, where you have to bother? You have to bother only in cases of operations whose range is greater than or equal to 2. Now, you begin. So, this loop actually find out the best step for operation OI. Like we have already done for the multiplication operation, already we have seen that this O6, the best step was here. So, that is what will be found out by this algorithm and in the first step we are actually this each type of operation. So, here we have started with the multiplier in the example case if you consider. So, you start for this multiplier for each operation you have to do. In this case we have started with the multiplier operation in the example, then for each j in the interval I, then what it says, then what you have to do, we have taken this operation. Now, you have to see in each step which is in the actually interval of this operation. In this case it is 1, 2. So, in each, that is what is being said, that in each interval each j, for each j which is the interval of I, you do what? You temporarily schedule OI in j and compute the value of cost due to fixing of the schedule OI and the changes of schedule of other operations due to data dependency. So, what does it mean? So, it means that you schedule. So, you take this one, you take O6 multiplier, that is the first operation type, then you actually in both the ranges. So, you schedule this guy over here first. Okay, that is what it is being said, that you temporarily schedule OI in this and compute the value of cost due to fixing of OJ and changes in schedule of other operations due to data dependency. So, if you schedule this over here, so this can be scheduled here or here, no changes, here is also no fixing and no fixing. So, this one will be there, but you have scheduled it over here. But sometimes it may happen that if you schedule an operation in a time step, other things may get constrained and it may have to be hard coded and then you have to find out the cost. Okay. So, now in this case what is the cost over here? It is 1 plus 1 plus 1. So, instead of 0.5 it has now become what? So, this cost is actually 3. So, you have to record this cost. So, you have to record this cost in some variable that is k nu. Okay. So, now if k nu is less than k best, assign assign the value of k nu to k best. So, initially we have started with k best as infinity. So, k best was infinity and now we have got the value of 3. So, obviously this is the k best, this is the case. So, you have to apply k nu which was 3 to k best and time step as j. So, you apply, so you find out this is there and you schedule it over here. Okay. So, this is the first step. Okay. Now, again you come back for each interval. Now, what do you do? Now, again you have to repeat because this is also in the interval. Now, you forget about it. Now, you schedule it in this interval. Now, what is the cost you will find? The cost you will find is 1 plus 1, it will be actually equal to 2. So, from 2.5 it has now become 2. Initially it was 2.5, then if you schedule it, it become 3. Now, if you schedule this guy in this second place where it is possible in the range, so it will become 2 and this one also become 1 plus 1, it will be 2. Okay. So, again we are actually scheduling in this interval. Initially we did at 1, now we are doing at stage 2. Now, in this case what is going to happen? So, sorry, in this case you are temporarily schedule y in step j, now it is 2 and compute the value of this one. So, in this case the computation value of k nu will be equal to 2. So, k nu is 2 and k best is 3. So, if this is the case, sorry, k nu is 2. Okay, and k best was 3 in the earlier case. So, now what happens? So, this is the case. So, assign the value of k nu 2 to k best. So, now your k best is 2 actually now here. Okay, now we will find out, then again we will go back to this loop, then you will find that the interval was only 1 and 2. So, your case is done. So, you find now what you do? So, you finally schedule OI in the base step and all operates due to data dependency. So, now what you actually have done? We scheduled it here and found out the value to be 3, that was the best. Now, we have again there was another interval where it could, sorry, another step which could be scheduled. So, now you schedule it here, then you find the best value to be 2. So, 2 is less than equal to 3. So, you schedule the value of O6 over time step 2 and you are done. So, this is O6 will be actually scheduled over here because that value is 2. So, that is done. Now, again it says that update all operations, everything, all the values you have to update it, okay, due to this data dependency, and because something will be freezed now, like you see, I already told you, because if you set this here, now this guy cannot be, this one O7 cannot be placed over here, it has to be placed only over here. So, all ranges etc. everything will be changing. Now, its range will be 1 because its interval will be 3 3. So, it will be only 1. So, this range will change. So, all these computations like a cost etc. like interval, range, probability, least cost, everything will have to be redone, and again you do, again you come to this loop and then you start doing for another operation, maybe for adder, maybe for subtractor or divider. So, this is how it happens. Okay. So, let us, I mean, just look at the example. So, initially this was our example. So, this range etc. has already been given over here. So, in the example, k1 represents a multiplier, 2 represents a divider, 3 represents a subtractor and 4 represents an adder. So, probability of 1 1 2 1, first we are trying for the multiplication. So, probability of 1 1 already told is 1, then probability of 1 2 1 is 1, okay, so 2 1 is actually 1. Why? Because these things have to be hard coded over there, and then probability of 6 1 is 0.5, that is 6 can be scheduled over here is 0.5, and then again probability of 1 2, that is probability of 1 2 is this one. So, sorry, 1 probability of 1, this is 1 in 2 will be actually no longer there. Okay. Probability of 1 2 is 0. Why it is 0? Because operation 1 cannot be scheduled in time step 2. We are actually considering only for 2 time steps over here. You should actually see for all the other time steps, because it is irrelevant, because the multipliers do not get any concern in time step 3 and 4. The multipliers are only limited to time step 1 and 2. So, we are actually listing for time step 1 and 2 over here. So, probability of element 1, that is operation 1 in one step is 1, 2 is 1. What does it say? That is operation 1 probability in time step 1 is 1. Operation 2 probability in time step 1 is a 1, and again operation 1 in time step 2, that is actually not possible, because 1 cannot be scheduled over here. So, that is what is written, and similarly 2 2 is also 0, because 2 cannot be scheduled over here, and this one is 0.5, and similarly 6 2 is also 0.5, because 6 2 can operation 6 can be also scheduled in time steps 2. Okay. So, this is how it has been calculated, and the list is actually, what is the list for time step 1? It is O1, O2 and O6. So, what does the list mean? The list means that O1, O2 and O6 can be scheduled over here, because we are only taking care of multiplication. Okay. So, this is how we have calculated. Then list of 1 2. So, list of 1 2 will be actually only 1, 6 will be there here. So, it is only 6 over there, because only 6 and there is only one multiplier that may be possible over here, and similarly we can find out the cost is 2.5 and the cost here is 0.5, already we have told you. So, we have already shown this is how you generate the cost. Okay, this is how everything has been done over here. Now actually what we do, now we have freedom of scheduling O6 in O6 range 2 in time step. If you schedule in time step 1, then actually what happens, the cost is 3. So already we have told, if the cost is 3, then base step is 1 and the base is 3. That is the first step when we are scheduling O6 in time step 1. Then what we do, then we actually schedule, can also schedule O6 in time step 2. If you do this, these are the values of probability values, these are the least values, and the cost will become 2, as already we have seen. So now we have seen that 2 is actually less than 3. So the base step is 2, and there is no more range where O6 can be scheduled. It can be scheduled only in 1 and 2. So we stop over here and we actually schedule O6 in O2. But now actually O7 will lose its flexibility. So now this guy will be have to be scheduled over here. There is no this thing over here. Now again you are actually having these two which you can play with. Okay, so if you again this part is fixed. Now you have to think of this adder and the subtractor. So you can find out that very easily. You will be finding out that if you put the subtractor can be put over here and put over here. If you put the subtractor over here, the cost will be higher because the probability of subtraction 1 is 1 over here, and if you put it here, so it will be 1 plus 1, it will be 2. But here if you put it, it will be 1 only, because this is 1 and this can be 1, and again if you put the subtractor over here, the probability will be 1 and the cost will be 1 over here. Okay, the cost will be 1 because there is no subtractor here, no subtractor here. But if you put the subtractor in time step 3, so it will be 1 plus 1, it will be 3. So your FDS will put the subtractor over here. So if you put the subtractor over here, then again this guy, this adder, will have a flexibility of here, here and here. Now you will be easily able to find out that. Again you will find out that in this case there is no other adder over here. So you can either, it will be placed here, here and here, because everywhere the cost will be 1. So your adder will be placed over here. So your adder will be here and your everything will be actually done. So these are all the values of the calculations which we have done, probability for this operation I power 3. So you can see that this subtractor is probability is 0.33, 0.33, 0.33 it is showing. So if you it shows that among the operation, if you schedule O8 in time step 1, then this will be the value. Okay, so if you schedule O2 in time step 2, the cost is 1. Okay, if you schedule O8 in time step 1, the cost is 1. If you schedule O8 in time step 2, the cost is 1. But if you put O3 in time step 3, already you have seen the cost becomes 2. So that is not good. So you will schedule O8 in either time step 1 or time step 2. So in this case, let us schedule this one in time step 1. Now it is left to the adder. Similarly, you will be able to find out that there is no more adder. So the cost will be 1 wherever you put in time step 2, 3 or 4. So anywhere you can put it. So the final step O8, O9 will be actually placed over here, so that you can easily visualize. And finally, we maybe note that whatever we got over this one, adder will be here. So whatever we got is actually same as the optimal solution we got by merging as soon as possible and as late as possible manually. So what we had done, we said that this part of the circuit we apply as soon as possible, sorry, as late as possible. This we apply as late as sorry, this is as soon as possible and this is as late as possible. You individually do that and you get the optimal solution. But here we did not do anything like that. Automatically the algorithm actually settled out in a settled out in a schedule like this. Okay, so what do we find out that? So force directed scheduling, actually it takes motivation from the hybrid nature of as soon as possible and as late as possible, and it will automatically find out places where which has to be applied, and it actually does it for you. Okay, so that is what is a force directed scheduling. So this is another heuristic, so which actually takes care of your hybrid nature. Sometimes as soon as possible is better, sometimes as late as possible is better. For a more general class of circuit, force directed scheduling is better. But still you can find out some examples where force directed scheduling also will not give you a most optimal solution, because all of them are heuristics and we are trying to gain our time by finding out a near optimal solution rather than going for a very complex algorithm. And all the three algorithms we discussed today were basically time constraints. So you have to fix up the time. Okay, we are not thinking about the number of resources. Based on the time step 3 or 4, among that we are trying to reduce the number of resources. For example, like if you are saying that in time step, I have taken time step 4, but I take 3 multipliers to do the job, and somebody I also take 4 time step to do the job, but I will take 2 multipliers to do the job. Obviously, we will go for the second person. That is what is being tried by this 3 algorithms we have studied. The time is fixed. Based on the time, we are trying to reduce the resources as much as possible. So, in the tomorrow's lecture what we are going to do, we are actually sorry, this one is your last schedule. I mean, I should show this is the final output of your this thing. So, the next thing what we are going to do, the next class we are going to go about list scheduling, in which case it will be more about resource constraint scheduling. So, the resources will be fixed, and depending on that you will have to go for whatever timing, I mean whatever minimum time you can achieve for that. Thank you.